All right. Hi, everyone. Welcome to the third seminar in our WRRC Spring Seminar Series. We have a general theme of the Red Hill water crisis. And this week, Robert Whittier and Donald Thomas will be talking about groundwater flow in the Moanalua, Red Hill, Halawa region. Robert Whittier is a geologist with the Hawaii Department of Health Safe Drinking Water Branch. And an affiliate faculty at Manoa Department of Earth Science and WRRC. And Donald Thomas is a member of the faculty at the Hawaii Institute of Geophysics and Planetology at and serves as the director of the Center for the Study of Active Volcanoes at Hilo. Without further ado, I'll turn it over.
Well, thank you, Carrie. Here's the structure of our slide, where we'll be talking about structures. First, talk a little bit about background, go over the problem statement, talk about the geologic setting of the study area, and the structures that influence groundwater flow trajectories, and an alternative approach in general chemistry to evaluate groundwater flow trajectories, and also a planned comprehensive regional geologic investigation to answer the currently unanswered questions. Okay, for background, both Don and I have been involved in Red Hill for quite some time. My first involvement was in 2006, working as a consultant for the Navy. And as part of that work, I did the contaminant flow and transport model, or the contaminant transport modeling, and also set up and executed a regional groundwater monitoring and aquifer testing study. Then in 2014, of course, we had a release, and I was at the Department of Health at the time and got involved in the oversight end of Red Hill. And we also invited Don to assist us due to his in-depth knowledge of Hawaii hydrogeology and groundwater. So here's the overarching question, and that is, how do we assess the risk of contamination from any source in a realistic way? Specific to this problem is for Red Hill, how to assess the risk from free phase and dissolved phase petroleum contamination to groundwater and to public drinking water sources within the area. And at this point in time, we can't state with certainty the rate or direction of groundwater flow, and thus we can't state with certainty the rate and direction that contamination will move. Key to gaining this understanding is looking at the geologic structures that influence groundwater and contaminant transport, which currently is incomplete. So this diagram on the left actually shows our problem. We have a potential source of fuel contamination, and hydrocarbon fuel is light relative to groundwater, also is immiscible in that it doesn't mix with water. So it's referred to as a light non-aqueous phase liquid. In small releases, we can retain the LNAPL, or that free product phase, within the vadose zone, but due to recharge, we'll get contaminant migration, the dissolved phase, to the water table. In a large release, which is definitely potential at the Red Hill facility, we can get both the dissolved phase and the LNAPL phase down to the water table, at which point the plume will spread and structures that are present at Red Hill that exert a significant control on the degree and direction of spreading. And currently, how these structures influence groundwater flow and the resulting groundwater flow trajectories beneath Red Hill and in the region are not well understood. We borrowed this diagram from the Navy's conceptual site model for Red Hill, and it actually shows our problem. We have 20 very large underground fuel storage tanks that are situated within the rock of the Red Hill Ridge, bottoms of which are about 100 to 150 feet above the groundwater, and that groundwater is a primary drinking water aquifer for the island of Oahu. To the northwest, we have two we have a primary drinking water source, and also to the southwest, a primary drinking water source. These two drinking water sources are shafts, which are basically tunnels excavated along the water table, distribute the pumping over a large area, and reduce the risk of saltwater intrusion, resulting in chloride fouling of our drinking water source. Unfortunately, the water table is where the LNAPL reside, so that increases the risk of impactful contamination from any spill at Red Hill to these type of drinking water sources. To the southeast, we have conventional wells, and they draw their water from deeper in the aquifer, so less susceptible to petroleum contamination, but nevertheless need to be considered. We have the basalt, which we've talked about previously, but also low permeability structures, which we'll talk about in more detail. Saprolite and valley fill in between the ridges, and also at the toe of the Red Hill Ridge, late stage volcanics, which resulted in explosive eruptions and the associated structures, subsurface structures with those explosive eruptions. So looking at a geologic map of the area, we have the Red Hill facility to the northwest and southeast. We have valleys which are filled with alluvial valley fill and underlying saprolite, poorly permeable structures. Also to the northwest, we have several primary drinking water sources, including the Halawa shaft, which again draws its water from right at the water table. Going Mauka to Makai, or from mountain to ocean, we will encounter a structure called caprock, which is a composite of marine deposits, beach deposits that extend down into the water table, and generally viewed as poorly permeable, but can have some highly permeable sequences within that structure. Also is the late stage volcanics and the associated tuff rings, again, poorly permeable and right at the toe of the Red Hill Ridge. If we look at the groundwater elevations going from the southeast to the northwest, starting here at Kalihi Valley, they tend to step down going from ridge to ridge. This gives us a hydraulic potential for groundwater flow and thus contaminant transport from the southeast to the northwest. But the other explanation for the step down is the semi-compartmentalization for the valley fill. And we also have late stage volcanic lava flows overlying some of the valley fill in the Kalihi and the Nu'uanu Valley. So the relationship between groundwater and the valley fill and saprolite sequence has been considered for quite some time. In 1942, Wentworth looked at the relationship between the valley fill saprolite sequence and the underlying basalt and groundwater, and come up with two potential realizations since it didn't have boreholes to ground truth it. One would be shown here as the shallowest extension of the valley fill into the aquifer. And it shows that only in Moanalua Valley would we get any significant extension of the valley fill into the aquifer. In the North Halawa Valley and South Halawa Valley, very little extension of the valley fill saprolite into the aquifer. But he also reasoned that if you look at the slopes of the valley walls and extended them downward, we could get a much deeper intrusion of the valley fill saprolite, very deep in Moanalua Valley, less deep, but still significant in North and South Halawa Valley. And this is at a cross section at the 500-foot elevation along the axes of the various ridge lines. Later, Menck in 1980 considered the effect that caprock may have on groundwater flow. And he reasoned that caprock is generally a poorly permeable structure and that it would divert groundwater flow from a direct Maui-type flow path to a flow path following the groundwater elevation potential from Honolulu to Pearl Harbor. And he estimated that minimal groundwater flow in this direction, but about 10 to 15 million gallons per day across this boundary here from Honolulu into Pearl Harbor. If that is correct, that puts the ground drinking water sources to the northwest at a significant risk to contamination originating at the Red Hill facility. More widely accepted groundwater flow trajectories in this area is that in many USGS publications that reason that the valley fill saprolite divide the Honolulu aquifer into sub-aquifers or compartments, and that the general groundwater flow would be in the Maui direction. And this is as described by Hunt in 1996. But he added a caveat. And he said the effectiveness of these barriers would diminish going inland and that their penetration into the underlying basalt would also decrease going inland. So the Menck, referred to as a Menck conceptual model, and the Hunt conceptual model are not necessarily mutually exclusive. If we look at going down South Halawa Valley, look at the possible structures that the groundwater flow would encounter and the possible directions of groundwater flow, we can see some very different risk contamination scenarios. Groundwater flow is Maui. It will go from the permeable basalt and then encounter the low permeability of the saprolite and the valley fill. And in some cases also encounter the subsurface structures associated with the late stage volcanics. Finally encounter the caprock, again generally viewed as being poorly permeable, but can have zones of high permeability, such as reef limestone layers and associated dissolution channels. If we go from the southeast to the northwest, depending on where that groundwater pathline originates, we can have an unimpeded pathway from Pearl Harbor or from Honolulu to Pearl Harbor, or an increasingly impeded flow path where groundwater would have to flow beneath the saprolite valley fill sequence. So two very contrasting risk implications depending on which groundwater flow scenario is most accurate. If we look at groundwater elevations within the facility itself, and this was groundwater elevations taken on December 23rd, and I have the year wrong, that'd be 2021. We see that during a period when the Red Hill shaft has shut off, as was done following the November 20th release, that we have almost no groundwater gradient potential going down the axis of the Red Hill Ridge. We have a 0.02 of a foot groundwater elevation drop over a span of about 0.7 kilometers. That actually is within the realm of uncertainty of the measurements. We do have a decrease in groundwater potential going to the northwest, which is fairly significant, about 0.2 feet. That would imply groundwater flow in this direction. However, if we look at the southeast side, we have an almost identical drop in groundwater potential going to the southeast. So it is very difficult to ascertain groundwater flow directions in Red Hill based upon groundwater elevations and relative groundwater elevation potential alone. So again, the depth of the valley fill and the saprolite wedge is one of the keys that we need to understand groundwater flow trajectories within this area. So to that end, the Navy, working with Boise State University, conducted a seismic survey to image the contact between the valley fill and saprolite wedge and the underlying basalt. And so these lines show the transects that were done on South Halawa Valley and North Halawa Valley. And my interpretation of the depth of penetration into the aquifer shown in percent of the penetration into the down to the midpoint of the transition zone of the freshwater lens. So the red line is where we would first see the contact of the basalt saprolite interface at the water table. The red line is that point at which that saprolite valley fill extends 50% into the freshwater lens. See that we start seeing some protection right adjacent to the tank farm. And we do see protection extending up to about even with the Halawa shaft. But this is very shallow intrusions down to about, okay, here's about the 25% penetration point down here, which is near the bottom end of the fuel facility and well below the location of the Halawa shaft. If groundwater flow is to the northwest, then there is a limitation to the protective nature of the saprolite valley fill. Here is an actual transect, seismic transect that was taken right adjacent to the Halawa shaft in North Halawa Valley. And it shows the saprolite valley fill contact extending to about 20 feet below sea level, or about 40 feet into the freshwater lens. So the next structure that we need to consider is the late stage eruptions in the tuff rings. And these are structures that are associated with the late stage volcanics located here at the toe of the Red Hill Ridge and also extending into Moanalua Valley. For Maui-type flow, it does present a further barrier, but we could get flow around it. But the extent of that resistance to groundwater flow depends on the nature of the structure beneath the surface of beneath the ground surface and into the water table. So here is a conceptualized cross section of the Salt Lake tuff ring complex along this transect right here. So we have what we refer to as a diatreme, which is basically the explosive vent where all of this rock got ejected and then much of it fell back in. We have the air deposits of the volcanic tuff ash on either side, but they are primarily surface structures. the late stage eruptions actually require some sort of plumbing to get the magma up here into the groundwater to result in that steam generated explosive eruption. And that would probably be a dike, another potentially vertical planar type structure that would be a barrier to groundwater flow. So to look at that, these structures have varying densities. We can look at the subsurface density using gravity measurements. So DOH and University of Hawaii and DOH did a seismic gravity study, looking for gravity contrast. On the light end would be saprolite, tuffs are a little bit denser. Basalt would be more in the dense intermediate range, and finally dikes and other intrusives would be at the high end. Diatremes have not yet been defined. And here was a result of that. The warmer colors indicate positive gravity anomalies or denser subsurface structures. The cooler colors, negative density anomalies or less dense subsurface structures. So the positive density anomalies were present directly underneath the Moanalua crater, within the base of the Moanalua Ridge and Moanalua Valley. The negative or less dense structures, ironically, would be within the Salt Lake crater, which is in contrast to Moanalua crater, also within the southern part of South Halawa Valley and the lower part of the Red Hill Ridge. So what does this mean? It means it provides possible evidence of dense structures and aquitards here in the Maui flow path, and also provides an alternate hypothesis for our flat water table beneath the Red Hill facility. So we've looked at structures and it's not totally answered all of the questions. So an alternative approach would be look at the groundwater chemistry. And this is something that I'm pursuing as part of my job at the university at looking at the overall risk of public drinking water sources to contamination. So this is a multi-step process. First, look at what groundwater species are commonly measured and use them as tracers. Establish their concentration in a natural setting as a baseline. That would be the unimpacted recharge zones. Then model the chemical distribution in groundwater and compare the model results with the measured data and look for zones of enrichment and depletion. So we're looking at land use influence versus groundwater chemistry. For our two conceptual models of groundwater flow, the Maui flow would be under non-developed land, so the chemistry should be very similar to that of the upslope recharge areas. If we look at Honolulu to Pearl Harbor, it's an urbanized area, so then we should be seeing anthropogenic impact. Two preliminary tracers we've looked at is chloride, comes from rainfall and dry deposition. Anthropogenic source would be irrigation with groundwater, and another natural source near the coast would be saltwater intrusion. Nitrate results from atmospheric deposition and rainfall, the decay of organic matter, which should be at a steady state in the upper recharge zones, and anthropogenic sources would include fertilizers and wastewater. So our goal here is to compare the site chemistry with that of upslope recharge areas of groundwater. Looking at chloride, the approach we took was chloride mass balance, in that we have atmospheric rainfall deposited chloride. the rainfall will get evaporated, increasing the concentration of chloride in the recharged water at a predictable rate. And so we do a mass balance approach. We can then estimate the concentration of chloride in the recharge and put that into a groundwater flow model. So to validate this, we have a climate station here right out my office here at the Upper Pearl City, and do a water balance study and estimate recharge, and also collect the rainwater to get a chloride composition of rainwater and dry deposition. So when we did our water balance study calculation, we got a recharge concentration of 25 milligrams per liter. We also have a lysimeter for collecting soil water. So during periods of recharge, collected soil water at 90 centimeters and got 20 milligrams per liter. So a very close agreement. Put that into our groundwater model, because not only do we have a climate station lysimeters, we have a well right outside of our office. So collect a sample from the well. Chloride is about 18.5 milligrams per liter. The model chloride for that same well is about 19.8 milligrams per liter. So we seem to have good agreement there. So this map shows the distribution of rainfall and dry deposition chloride in recharge. The inset shows the Red Hill area, and the arrows show our two conceptualized groundwater flow trajectories. The average recharge concentration of chloride above the facility would be about 39 milligrams per liter. So that means for a Maui-type flow, the groundwater should be less than 39 milligrams per liter. But if we go from Honolulu to Pearl Harbor, then we're flowing through areas of greater chloride groundwater recharge. So then our groundwater chloride should be greater than 39 milligrams per liter. So we put this in a groundwater model, map the results, but map them as excess chloride, which is a percentage of additional chloride measured versus that the model predicted based on rainfall and dry deposition. We validate that model using those wells that are in the conservation or primary recharge areas. You got pretty good agreement with the model, so it does seem to work. And if we look in the Red Hill region, we do see some wells that where the groundwater chlorides do agree with that predicted by the model, but overall we have significant excess groundwater chloride. This would be inconsistent with Maui-type flow. So the next question is, where does that come from? We have a major pumping center, and one hypothesis would be that that pumping center is drawing chlorides from deep beneath it up into the freshwater lens. But we have a series of wells that have multiple depth sampling points. And if we look at that, chlorides in the water column versus the average of chlorides measured at the Red Hill shaft, we cannot account for what is pumped versus what is in the water column beneath the Red Hill facility. The Red Hill shaft chlorides vary from about 75 to 147 milligrams per liter. And that seems to vary positively with pumping, in that as you increase pumping, you go to the higher chloride concentrations. So if we're not getting the chlorides from directly beneath, whereas it's coming from, One possibility is that the we have layering of our lava flows. The different sequences or types of lava in those flows has very contrasting hydraulic properties. We have clinker zones, which if they're unweathered would have very high hydraulic conductivity, but we also have layers which very massive lava, very low hydraulic conductivities. So we would have a structured preferential flow path down dip of the lava flows, potentially extending into the transition zone. So that would potentially result in groundwater being drawn up to what we've often thought of as a skimming shaft at the water table surface. But implications for Red Hill would include a capture zone that extends much further downslope than would typically be modeled. Also, it'd be much broader. But one of the more critical points would be that this would be the Red Hill shaft would be much less efficient at capturing shallow groundwater contamination. Finally, nitrate as an anthropogenic tracer. And go quickly over that. In 2006, Houghton et al. Found an inverse relationship between rainfall and leachable nitrogen in the forest setting of East Maui. We looked and see if that was also applied throughout other islands throughout the state and found a good correlation, inverse correlation between rainfall and nitrate concentration in the wells if you do a rainfall weighted average of rainfall along the flow path. So again, we modeled the nitrate and mapped it as a percent exceedance of the measured versus the modeled. In the Red Hill region, we find that we have actually some depletion, some agreement with the model, but then some zones of significant excess nitrate. So it's two very different patterns of nitrate with different flow trajectory implications. So what this brings us to is that chloride concentrations observed are inconsistent with the Maui flow trajectory and actually more consistent with the alternative Honolulu to Pearl Harbor. Nitrate story is more nuanced, and that is due to potentially biodegradation of fuel hydrocarbons, which will reduce the nitrate in the groundwater as the indigenous microbes break down the fuel and hydrocarbon contamination. We'll continue to work with nitrates and nitrate isotopes to refine our interpretation. And at this point, I will turn it over to Don and let him shift the screen sharing to him, and he will talk about what additional work we're going to do.
So Bob has talked about data that we all have gathered over the last several years to better understand this system, but as he has said many times, that there is still a great deal more that we need to do and to learn about this entire system before we'll be able to accurately estimate risks associated with releases of contaminants into the groundwater here. And so we put together a program of planned studies that we would like to accomplish to help us answer some of these critical questions. Very briefly, I'll go into more detail here momentarily. What we want to do is better define these major structural features, the valley fills, the diatremes, the other large-scale structures within the Red Hill region that have very substantial effect on groundwater transport and how contaminants are likely to move. We also want to better document and characterize sort of the intermediate scale features within the basalt ridges. The pahoehoe, the a'a, the clinker, and the soil and clay features will have significant impacts on how both groundwater moves as well as LNAPL will move through this system. We want to document the interaction of fuel with basalt. The fuels are hydrophobic and they will react differently with the basalts than water typically does. And so we intend to develop a better understanding of how that interaction will impact how that fuel migrates from the beta zone, from the unsaturated zone, into the water table. We want to characterize the natural and pumping induced flow rates and directions at a variety of scales in this region. And with that data, we'd like to populate a 3D geologic model with the site-specific data, apply some geostatistical analysis to what we see there geologically to develop a really detailed conceptual site model, and then use that conceptual site model to drive the development of a numerical flow model, both for the LNAPL, for the fuels, as well as for groundwater, and use our existing data set of so-called synoptic data, water level data, and tracer data to validate that numerical flow model. So I'll talk in more detail now about each of these types of studies and what we hope to do and hope to accomplish. First thing we want to do is image the valley fill and saprolite wedges. We know that the valley fill and saprolite are much less permeable than the basalts. We would like to, they are also heavily altered, and they respond to seismic waves quite differently from the basalt itself. There's a technique that's been used on Oahu called ambient surface wave tomography. It's a seismic, passive seismic method. It was successfully used in Southeast Oahu, looking at the sediment fill and basalt in the Sandy Beach region by Niels Grove and his colleagues, and was quite successful at it. The technique employs natural seismic activity or seismic wave activity is generated actually by waves impacting on the shoreline, as well as anthropogenic seismic noise that's created by traffic and quarry operations and similar types of what we call seismic noise, and allows us to develop a map of seismic velocities over a range of depth slices. This is a result of Niels Grove's team out near Sandy Beach, and each of these images is a horizontal slice through the geology of the area and allowing them to identify the seismic velocity and then infer that the zones where the seismic velocities are higher are the zones of more pristine basalts, and differentiate those from the lower seismic velocities, which are likely sediments. We would like to apply this technique here in the North Halawa Valley and South Halawa Valley to develop a very detailed picture of how deeply incised those valleys were and how deep the alluvium and saprolite is able to penetrate into the water table and affect groundwater flow. Again, this idea we have, and one of the things that I wanted to mention too, is that having wells into these features will allow us actually to ground truth this interpretation. And there are a number of wells, there will be additional wells drilled in this region that will allow us to really much better characterize both the saprolite and valley fill intervals, as well as in the vicinity of the diatremes of these late stage volcanics. The other technique that we want to apply is additional gravity surveys and try to better image the intrusive lavas that are associated with the Salt Lake Tuff Ring complex. Bob has already showed this image indicating that we have higher density material up in, excuse me, up in this region, and also extending over here and under the Moanalua Valley, as well as partially under Red Hill Ridge. And our intention is to expand this survey area and increase the density of seismic stations so that we can get better resolution. One of the things I wanted to point out is that in these gravity anomalies, the solutions are non-unique. There are a number of different conceptual models for these intrusive bodies that will satisfy the same data set. By increasing the number of data points, we can narrow those down. We will also investigate using this passive seismic surveys over the region of these high density features to try to better image those as well. The third step in defining these major structural features is to compile all of the existing and new well core data. We have a number of wells that have been drilled in this region. This shows an array of wells. The ones with the kind of the light blue labels, these are existing wells that have been drilled using a technology called continuous coring. And so we have actual geologic samples over the entire depth of the wells here that have been drilled. We also are in discussion with the Navy on drilling some additional wells in this region that will really give us a much more detailed data set that we can compile into the models, the geologic models for this region, that will give us much better insight into how the groundwater flow will interact with these different lava types. Now, let me move on. So we want to characterize the intermediate scale features within this area as well. And what do I mean by intermediate scale? I'm talking about the individual lava flows. This is an image taken from a recent USGS publication that gives us kind of a conceptual idea of what the lava flow sequence looks like. We have the flow units that can be several meters thick and up to 10 and 20 meters wide. And these flow units are typically surrounded by clinker. And within this sequence, we also have Pahoehoe lavas, and groundwater flow through these individual features can be quite different. So our intent here is to try to better image these different flow units using electrical resistivity tomography and audiomagnetotelluric surveys. And we would be looking specifically at the individual ridges in this area. We should be able to image and distinguish the weathered clinker zones from the cores and from the Pahoehoe flow intervals as well. The area in which we would conduct these surveys is along Red Hill Ridge. This is a view downward on Red Hill Ridge. The tanks themselves are down here. They would make it impossible to apply this technique below the tanks because this is an electrical method, and the steel tanks would disrupt the signal that we would hope to gather there. But further up the ridge, we feel like that information will give us considerable detail on the array of Pahoehoe and clinker zones that we have buried within the ridge below the tanks and down into the water table. Likewise, over here on the Halawa Ridge, just above the quarrying operations. Another aspect of characterizing these intermediate scale features, and really what we're trying to accomplish with this characterization, is to identify where flow can occur and try to develop an understanding of what the scale of that flow would be. And so we will conduct a sequence of measurements directly measuring exposed lava flow units and identifying the transmissive features in those flow units. We can do that using exposures inside of tunnels. There are a number of tunnels that have been cut into the ridges surrounding Red Hill, and where the interior walls of those tunnels are exposed, we can document cooling joints in the flow units, the void spaces, and the clinker zones. We also have exposed quarry faces. The Halawa quarry has been very generous in allowing us to come in and inspect the faces of the quarrying areas. Some of this work has already begun. Dr. Scott Rowland, who is with the faculty at the University of Hawaii, has mapped, in this case, these are the clinker zones. We have lava flow interfaces here, and although you can't see it very well in this image, if you look at this image, he's also mapped the cooling joints where fractures have bisected the core units, and developing a statistically significant inventory of the distribution of these fracture units, determining what their fracture apertures are, will be able to model how fuel is able to pass through the vadose zone, the unsaturated zone, on its way down to the water table, and actually develop some models for that to be able to broadly understand how fuel does interact with these features in the subsurface and work its way down towards the water table. And finally, another method that we are going to investigate is there is a well logging technique called borehole televiewer, where we can actually go in and image the exposed walls of an open borehole and image not only this is a core taken from a borehole. This is a borehole televiewer image, not of the core itself, but of the borehole walls. And we can image the clinker zones, we can image the fractures and document the frequency of these fractures, what their orientation is, and their apertures, and also input that into our model. So the next series of studies is to document the fuel and basalt interactions. What we want to do is assess the retention rate of fuel by different basalt morphologies. What I'm saying here is that when you say pour a gallon of fuel onto a basalt surface or a soil surface, that underlying soil, some of it will adsorb and hold on to that fuel. Likewise, the basalt will hold on to some of that fuel. And so a spill of a certain size, as Bob mentioned early in the presentation, may not even make it to the water table. And so what we want to do is understand how much fuel is retained in the vadose zone and how large a fuel release would actually make it down to the water table and form this LNAPL plume on top of the water table. And this will mostly involve laboratory work, and we'll be using weathered and unweathered samples of the massive the clinker and the Pohoroi to do these studies, and looking at them wet and dry, because the level of moisture will also affect the rate of retention of the basalt for the fuel. Ultimately, what we hope to do then is assess the rate of transport through massive and fractured core lavas, and do modeling of fracture apertures and fracture frequencies to determine how that fuel is moving. And we know that is a very complex process. This is an image taken from a study in hard rock environment elsewhere, but you can see the fuel distribution is nowhere near, in the red and blue, is nowhere near contiguous. It's a very scattered and tortuous pathway that the fuel does follow through these fractured hard rock environments. So it will be a combination of laboratory studies as well as modeling. The next set of studies, we would like to characterize water flow under pumping and non-pumping conditions. This is something that we hope by taking direct measurements of water flow in some of the existing wells, they can provide us with at least initial very site-specific information on water flow and water flow rates and water flow trajectories that we can then use to develop a tracer test, a larger scale tracer test that will give us a regional indication of how groundwater flows. So the first step in that is conducting in-well measurements of particle tracks. This is a technique where we can drop an instrument into a well, either open hole or in the screened interval that allows water to pass through the well laterally. And the technique allows us to not only determine the rate of flow, the velocity of particles that are imaged in the flow system, we can also determine the direction. So this is this is showing data gathered from a specific well in the open hole section, and then in a screened well where there's only a short section open to study, and they show very similar results. Those results then are plotted up in what's called a Rose diagram. And although we don't expect any individual well to tell us what the regional flow direction is, by measuring these flow directions in a broad sequence of wells in this region, we feel that the preponderance of evidence will give us some information of what the rate of flow is and the overall direction of flow. Also, as part of this work, we want to expand Bob's analysis of the natural tracers to include ions, the ion concentrations such as the chloride, the other ions, the isotopic composition of the water and the dissolved ions that are both from natural products as well as anthropogenic contaminants that are already present in the water. And again, the idea is that water under urbanized areas has distinctly different chemical compositions and isotopic compositions than water coming in from more pristine regions. And with all of that data then as guidance, we will plan to design and execute a dye tracer study where we would inject a dye tracer into a carefully selected well and then monitor wells that, again, our preponderance of our data suggest is the direction of water flow. And finally, one of the things that we have not done yet is try to inventory the amount of water that is flowing within this region and is discharging into Pearl Harbor, because that ultimately would be the destination of this Malka to Mackay flow. And this would be following work that Eric Atias and colleagues did offshore of West Hawaii. What they were able to do is use an electrical geophysical method to image the electrical conductivity below the seafloor and identify a layer of freshwater saturated rock, as well as an area where that, whatever that confining layer was that was responsible for that deeper freshwater, allows it to come to the surface. So he was able to actually image the flow of water through the ocean bottom up into the overlying saltwater column. And so we would like to attempt some of these surveys within Pearl Harbor. All of these are, of course, subject to agreement by the Navy to allow us to come in and be able to conduct these surveys without interfering with their normal operations. Now, one technique that has been mentioned that we have discussed is the so-called self-potential method. This was used in that Southeast Oahu study. It did show an indication of direction of flow of water in that region. However, this is an electrical method, and within the region that we're working, there is a tremendous amount of buried electrical conductors, the pipelines, the tanks, and all of these will have an effect on the signal that is surveyed using these self-potential surveys. And so although we will attempt it, we don't have high expectations that we'll be able to get very reliable data from that exercise. The next step in these studies will be to integrate the well log data and the geophysical results. And what I mean by this, we want to put this into a 3D visualization model. This is an example of what can be done. These are actually a visualization of the geology in the areas surrounding the fuel tanks within Red Hill. When the fuel tanks were being constructed, they had geologists go in and map every single lava flow and describe every single lava flow in the walls of the cavity that was excavated prior to the installation of the tanks. And so we can put that into a three-dimensional visualization and apply appropriate geostatistical methods to extend and infill the intermediate scale structures where we don't have that site-specific data. And this is another example where that original data set was modeled to show the extent of Pahoehoe and A'a and clinker units within this system. And what we can do with that model then is to make a sort of at will various slices through this system and define the different flow units and their ability to allow groundwater and LNAPL to flow within this region. Ultimately, the goal of this effort, though, is to use that three-dimensional visualization to develop a comprehensive conceptual site model based on the most detailed geophysical and ground truth data and statistical modeling that we can generate. And then that CSM, that conceptual site model, will be the starting point for subsequent numerical models. And those numerical models will include an LNAPL transport model, a numerical model for modeling groundwater flow. The LNAPL transport model will be specific to the VADOS, the unsaturated zone. Numerical flow model will apply to groundwater flow through this region. And ultimately then that will form the basis for a contaminant fate and transport model. As I mentioned earlier, the intent is that once that model, and we don't develop these models in a vacuum, once we develop the models, we then validate those models using measured water levels over extended period of time for natural flow conditions as well as under pumping conditions. And then with that, we should be able to make much better estimates of groundwater flow within this region, compare those against also the diatracer test, and come up with the best possible model we can. And so in closing, what I am trying to sort of say in summary here is that this is a depiction of the flow model that was developed by the contractor for the Navy. It shows these very linear so-called particle tracks from beneath the tanks down towards Red Hill Shaft. This is looking at these data in map view from above, and this is looking at a cross-section of that flow. So a very narrow flow path being followed by particles in the water as they migrate down towards Red Hill Shaft. We want to transition that to one that recognizes the complexities of fluid flow through this extraordinarily complex geologic system, and will more accurately portray what happens when a contaminant is released within this region and how it would spread and travel both horizontally and vertically. And finally, I would add a postscript, and this is in anticipation of a question that I've actually been asked. Well, if the tanks are going to be shut down, why are you going to do all of this work? And my answer to that question is, what we don't know about Red Hill hydrogeology, we also don't know about most of Oahu's hydrogeology. We hope that the work that we're going to do here will serve as a template and a stimulus to expand our efforts to better understand how contaminants do move within the basalt formations here on Oahu, and what we can do to minimize the risks to our really vital drinking water resources on the island. With that, I thank you, and we can begin to take questions. Thank you very much.